All right. Welcome, Math 13 students. This is a final review of Chapter 8, a little bit of a summary. Pen is horribly dry. All right. So, and by the way, when I get into 8.2 and 8.3, I'll run through a couple of examples and we'll hit all the details as far as the calculator and the keystrokes go. So, 8.1, basics. You should be able to write the null and the alternative hypothesis given a particular kind of statement. If I ask you to write the hypotheses, you should be able to do that. You should also be able to identify the initial claim. This really comes into play in 8.2 and 8.3, but you gotta be able to identify the initial claim to write them, and you need to hold on to that detail. Now, that's really pretty basic, but you should also be able to identify the tail of the test. That would be the left tail. That's when your alternative hypothesis is written with a less than. It might be a right tail. That's when the alternative hypothesis is written with a greater than. It might be a two tail, and that's when the alternative hypothesis is written with the not equal. So you should be able to deal with that. So then, and that really truly is mostly vocabulary and the language. Now, once that's out of the way, there are things, numeric things, that do crop up in 8.1 that I can ask you to work with. You should be able to use a given p-value and level of significance that's the alpha to either reject or fail to reject the null hypothesis. So if I give you a p-value and an alpha, you should be able to take care of that. I'll remind you that when the p-value is less than or equal to alpha, we reject the null hypothesis. When p is greater than alpha, we fail to reject the null hypothesis. So you want to keep that in mind as you think about the notion of the p-value and the alpha. This is the criteria we use. Given a claim, specifically you need the alternative claim. So given a claim and a test statistic, I can ask you to find the p-value. So let me run through two examples here, one for each of these, and then we'll finish up with the numerics of 8.1. So, suppose you run a test and you have a p-value equal to 0.0407. And suppose further, for this particular test of hypothesis, we are using an alpha equals 0.05 or 5%. Sometimes you'll see it written as 5%. So the question is, do we reject the null hypothesis? I have to take my p-value 0.0407, 0.05 to figure out if my p-value is less than or equal to the alpha. And it is strictly less than. So yes, my p-value is less than my alpha. So we reject the null hypothesis. Suppose we change things around for the next little example. We leave the p-value as it is, but alpha is now 0.01. My p-value is now greater than the level of significance alpha. So in this instance, we would fail to reject the null hypothesis. So you've got to be able to compare p to alpha and come to the right decision. By the way, I don't know why that one makes me happy and that one makes me sad. No real reason for it. So let me give you another example. Suppose we've got the claim some sort of population proportion is more than, I don't know, pick a percentage, 75%. I'm not sure what we're measuring. The proportion of students who take stats. In stats, there we go. It's a little sloppy, but I'm sorry. It's more than 75%. So I translate that claim. P is greater than 75%. And suppose further, we've got a test statistic of big P, excuse me, not big P, test statistic of Z equals 2.13, 2.13. Find the p-value. All right, so I have to give you a claim. That claim has to be in the terms of the alternative hypothesis. I've got to be able to pick out the tail of the test. So this is a right tail test, and I can see that because of the inequality. My z-value is positive. So the way to answer this question and to find the p-value is to remember a couple of things. For the p-value, it's a probability. So I draw my distribution, the z distribution for proportions. I plug in my test statistic. That's the 2.13. That's that test statistic. The p-value, because this is a right tail test, the p-value is this area right there. That area is equal to the p-value. So the way to answer the probability question is to find the area. And this is where you've got to go back and remember the tool to use. From 6.1 and 6.1 and 6.2, normal CDF. So we want to find the probability that Z is greater than 2.13. That's our p-value. Let me jump over to my calculator. I'll go through the keystrokes, and then we'll move on. There we go. Get rid of that. So, second, oh, I'm sorry, I'm not sharing my screen yet. Yeah, I am. So second, distributions, normal CDF, the lower bound, 2.13, upper bound, 10, raised to the ninth. The mean is 0, the standard deviation is 1. Paste that in. So 0.1, sorry, 0.01658,166. 0.0166. And again, there's a number of videos already available in the Canvas shell that demonstrate this. So there we go. There is finding a p-value. Now, what else do you need from 8.1? What else can I ask you to find? I can ask you to find specifically the test statistic. There's two of them in question. One that's used for claims with proportions, and one that's used for claims with mean. So the test statistic. Now to find this, you need a couple of things. You need the claim. Specifically, you want the null hypothesis, and you need the sample data. For proportions, z is equal to p hat minus p. Down below we have p times q all over n, all within a square root. And for means, it's the t distribution, and it's x bar minus mu divided by s over the square root of your sample size n. And you can see that there's a part that comes from the sample in every one. I got to stress this every time I do this. And a part that comes to us from the null hypothesis. And I'll remind you, I suppose, here, that q is equal to 1 minus n. Can't know p and not know q, really. So those are the two things that I could ask you to find. I'm going to run through. The second one because the keystrokes are just a little bit more intense there. Population mean is, I have no idea what we measure. Oh, let's measure car speed. 65 miles per hour. That's on our local highways. So that's my claim. We have some data. X bar is equal to 68 miles per hour. S is equal to 3 miles per hour. N is equal to, let's make it 40. Find the test statistic. So I need my mean, I need my null and my alternative. Well, I really just need my null hypothesis. Sometimes they're given to you directly. Sometimes you've actually got to translate them. So there we go. There's my null hypothesis. So I need that little bit of information, and I need this right here. At that point, it's just a matter of plugging the detail into the formula. T equals 68 minus 65 divided by 3 over the square root of 40. This is one of the few calculations where students can be led astray with their calculator. But I think everything will turn out okay. So you notice there's a lot going on upstairs and a fair amount going on downstairs. So let me run over to my calculator and let me make that calculation. So I always take care of the numerator first. Now, I like to take care of this in one set of keystrokes. I'm going to use, because I can't help it, my grouping symbols. That's what they're there for. So there's the numerator divided by my standard deviation divided by the square root of the sample size. There's the test statistic. Suppose I had tried just 3 divided by 3 divided by and you see you don't get the same result. So you've got to be careful about some of these calculations. And this is really one of the very, very few where the order of operations really comes into play. If you want to try to do the whole thing, you can do it like that. Get everything going at once. The numerator now will be calculated separately. That's what parentheses say. If they say work here first, and there you go. But a lot of people have trouble with the numerator and the grouping. So I usually tell people just to do that separately and then hit the denominator stuff. But here you really do need the grouping symbols. It's one of the few times this semester you actually do. It's really weird. All right, so what did I say that was? No, I've lost it. There it is. 6.325. And there we go. There is the test statistic. About the only thing I will say is, remember, when you're working with a sample mean and a claim about a mean, the distribution we use is the t-distribution. All right, so that's really the detail of what people must know from the chapter 8.1 material. Now I want to run through some examples of what you'll see out of 8.2 and 8.3. So, great. Yeah, let me try it. I want to do it different. Sorry. Quite. Less than 16% of Californians have not had a COVID vaccine. Less than 16%. And we have some data. We have some data. X is equal to 29 and N is equal to 200. All right. And this is from a simple random sample. And I note that the details for a binomial distribution are satisfied. 16% of 200 is 32. So both P and Q are well above the 5 required for the requirements. I very rarely ask people to check requirements on claims about a proportion. But I do on claims about a mean, because that's just a little bit more straightforward. So let me go ahead and deduce the claim and the initial claim. P is less than 16%. I see that right there. That tells me I have on my hands the alternative hypothesis. So H1, P is less than 16%. The null hypothesis, P equals, I know greater than or equals, but we write equals 16%. It's the complementary case. I'll clean that up when we get to the next page. This is my initial claim, and I'll just note that also. The only other thing I need is my level of significance. I am going to use an alpha equals 0.05 level of significance. Now, if I ask you to do a problem like this on a quiz or on an exam, I honestly expect you to use the p-value approach. We're going to test that claim. I will note that x is equal to 29, n is equal to 200. And we've got the null hypothesis, p equals 16%. We've got the alternative hypothesis, p is less than 16%. That's my initial claim. All right. So once I get that down, I note that I've got a left tail test. Actually, I noted that on the previous page. I just didn't say it out loud. And I'm really ready to go ahead and take care of the test. So, one prop z test. P naught 0.16. X was 29, N was 200. We had a left tail test. We'll go ahead and calculate that. I need the p-value. There's my p-value, 0.2184 and change. I'll take 3 significant digits. It's a probability, 0.281. So once I compare it to my level of significance, I realize that my p-value is greater than my level of significance. So we fail to reject the null hypothesis. Now, the last step is to address the initial claim, and it goes like this. So at alpha equals 0.05, there is not enough evidence to support, and then we've got our initial claim. P is less than 16%. 1, 2, 3, 4, 5. 5 steps. They all have 5 steps. Same 5 steps. It's like baking a cake. So a test for a claim about a population proportion is really this straightforward. What do I ask you about on a quiz and on an exam? It's awful hard to get students to reproduce this on a calculator or a computer of some sort. So what I usually ask students to do is I ask students to find the p-value to determine whether the claim, whether H naught is rejected or failed to reject, determine if the initial claim is upheld or not. Another way I've said it is so anyway, there we go. Let me go ahead and take a look at the material now in 8.3. Material in 8.3 is very, very much the same. Here's another claim. The mean age of Hartnell students is 21 years old. We have some data. X bar is equal to 26. That's years. S is equal to 6 years. And N is equal to, let's make it 39. So we're going to test this claim with alpha equals 10%. That's 0.10. And we've got a simple random sample. So I'm going to test that claim in a moment. But one thing I would ask or could ask is, can we test this claim? Are the requirements met? There are only 2 of them, and I feel like should ask students to test or to check that this kind of a test meets the requirements. And they are a simple random sample, and we've got that. And then either or, n greater than 30, or a population that's approximately normal over the variable in question. And we've got the n greater than 30. So we're justified in reaching for our calculator. Otherwise, honestly, we need to leave the calculator in the box, or more likely find a better tool. We do have tools to use when these claims are not met, but that's a more advanced tool. Difference between a handsaw and a buzzsaw, I suppose. So let me note that. Let me note that X bar is equal to 26 years. S is equal to 6 years. N is equal to 39. Alpha is 0.10. All right. Oh, let me bring the one sheet back here. I need to grab one more thing off of this statement page, and then we can go on. What kind of a test do we have? Mean age is 21 years old. Looks to me like we have mu equals 21 years. Looks to me like we've got ourselves a two-tailed test. And I've been handed the null hypothesis. And I know I've got a two-tailed test because when I have a claim of equality, the contradictory or complementary claim is not equal to. All right, so there's my initial claim, the null hypothesis in this one here. All right, so I've got everything I need there. Now I'm going to come back over to my calculator. share my screen, make you go away. All right, so stat, test, t-test. I don't have raw data, I have summary statistics. We have a claim of 21 years of age. 26 is my sample mean. 6 is my sample standard deviation. 39 is my sample size. And we have a two-tail test. Calculate. Ooh, good. I've got a very small p-value. Now, you'll often come across these when you do statistics. This is it's going to be very, very easy to reject the test statistic. You'll notice, reject the null hypothesis. You notice a test statistic at 5. 5 is a large number compared to 0. The t-distribution hugs around 0 just like the z-distribution. So this p-value is an extraordinarily small value. You don't want to think it's like 7 and change. It's not. This is 7.00 times 10 to the negative 6. I'm going to note that. It's very common for students to think that they're looking at the number 7 for some reason. It's that e negative 6 I think they find puzzling. And that's your exponent. So 7 times 10 to the negative 6. You'll remember what that really means. And I don't expect anyone to actually write this out, because I wouldn't. You have to deal with it like this. 0.1, 2, 3, 4, 5, 6. That's what that equals. Oh my God. So 7.00 times 10 to the negative 6. 0.10 is the alpha on that particular question. So my p-value is way less than the alpha. So we will reject the null hypothesis. Then the last thing to do is to address the initial claim. So at alpha equals 0.10, data do not support mu equals 21 years old. So even though our initial claim was the null hypothesis, the one that turned out to be most likely was the other one. There we go. That's really what we need to be able to do out of chapter 8. The only other thing that you might run into, and you will at some point this semester, is claims that use raw data. So mean time to graduate at Hartnell is more than, there we go, 3.6 years. And it probably is. Let me make this one a little bit cleaner. It looks too messy. Sorry. What did I say? 3.6 years. And this particular example, I'm going to make it very brief because I'm starting to run out of time here. This is where I'll use raw data. I'll give you a sample to work with. So we've gone out, and we're going to assume for the sake of this demonstration that all the requirements are met, that we've got a simple random sample, and because it's going to be small, we're going to assume that grad time is normally distributed. So 3.7 years, 4.1, 4.3, 3.0, 2.5, 3.9, 3.9, 4.0. All right, so that's enough for my exam. Oh, let me give myself two more. 4.1, 4.2. So I've got my sample there. More than 3.6 years. Let me see if I can squeeze it in down here. H naught, mu equals 3.6 years. The alternative mu is more than 3.6 years. And you do enough of these, and honestly, figuring out the flavor of your hypothesis becomes easier and easier. And so I've got a right tail test with a mean of 3.6 years. I'm going to go ahead now and find my p-value. All that data has to be entered into your calculator. And we've got 3.7, 4.1, 4.3. 3.0, 2.5. 3.9, 3.9, 4.0. 4.1 and 4.2. All right, so I got my data set in there. List one, I've got to remember where it is. Pick up my t-test. This time I've got raw data. The claim was 3.6 years for the null hypothesis, list one, frequency one, and we've got a right tail test. You know what, this time I'm going to go ahead and select draw. We're going to get the p-value, and we'll get the test statistic. Ooh. So there's my p-value, 0.1873. There's my test statistic, 0.9341. So that value there, 0.9341, is the test statistic. The area here is 0.873. 187, 3 significant digits. There we go. Let me stop the share. So I will compare this to, oh, did I set an alpha? I did not. I'm going to use 0.5. And he's greater than that, so we are going to fail to reject the null hypothesis. And at alpha equals 5%, data do not support mu is being greater than 3.6 years. And now let me jump back to my calculator for just a moment. I'm going to point something out here. Let me come back and redo the test. Very easy to do. I'm not going to change anything. But this thing I'm going to hit calculate. And I like this because this gives me my summary statistics. And we had a mean of 3.77 and a standard deviation of 5.8, I guess, for that sample size of n equals 10. Now, the claim was that the mean was greater than 3.6. This is 3.77. 3.77 is bigger than 3.6, isn't it? So let me show you what's happened here. If I go back to that analogy that I was developing quite a while ago about the barnyard. So what has happened here, (3.6). Out here at 3.7 is my mean. The thing is, that's still within the close to mom area that I was mentioning. My data point would have to be farther away in either direction because it for me to go ahead and work with the alternative hypothesis. So we were still fairly close to the claimed mean and the null, too close for us to dismiss this. This is probably or more likely down to more normal variability. In any case, that's really what you need to know about 8.1, 8.2, and 8.3. I'm going to go ahead and stop the recording.